Alrighty, kiddos. We're going to wrap up 2.8 on the chain rule. And the end of the section is a bit of a doozy. We're going to first do a quick look at applying the chain rule to the trigonometric functions in general, see how that looks, and then look at a very specific application of the trig functions, specifically the sine and the cosine, as it relates to something called simple harmonic motion. So that's kind of the order of events for today. And let's stop talking about it and just be about it. So I do have a new setup with my camera, so I'm a little bit, I don't know, not worried. I won't say worried. It's going to be a little different. Oh, whoa, whoa, whoa. No, you don't need to see that. That's my, there we go. So you should be seeing my doc cam. The thing that worries me, oh no, they fixed it. It fixed itself. I was worried it was going to be flipped, but it's not. So we're going to call this 2.8 concluded. We can even do like a subtitle here. Chain rule for trig functions and simple harmonic motion. It's a doozy. No getting around that. But I have faith in you guys. So if you recall from yesterday, whenever you're watching this, we had the chain rule introduced, which allowed us to calculate the derivative of composite functions. That if we had some function that was an outer function and an inner function, a composite function, to find its derivative, we differentiate the outer thing, but then the chain rule has us pop out that inner function and differentiate that as well, which was really nice and useful when we had kind of nasty composite functions, especially like power functions, like we saw with like a fourth power. We could power this through the product rule and arrive at a derivative, but the chain rule allows us to say, oh, do the outer thing, pop out the inner thing, take its derivative. And then it's just critically important for when we're trying to do stuff like a 10th power. Like, are you kidding me? No way, Jose, are we going to do this guy by the product rule. That would take 8 years. And so that was nice. That was cool. It also allows us to turn rational functions into situations that are composite and maybe avoid some quotient rules. We did already kind of do an example or an illustration, I guess, of chain rule with sine. And so it works the same. We're going to write out kind of explicitly that this is okay with some just the definitions of the chain rule on the trig function, where specifically we're talking about trig functions whose argument, the thing that goes inside of the sine or the tangent or whatever, is itself another function. Okay. If it's just sine of x, well, then our derivative is just cosine. There's no chain rule there. But if it's sine of x squared plus 3, then we got a chain rule, okay? Because x squared plus 3 is itself a function, so this is a composite function, so that's when we pop out the inner derivative. And that holds true for all of our trig functions. So I think I'm just gonna write that down just so it's on your paper, we know that it's true, and then we'll do a couple of examples with chain rule and trig functions. Okay. So chain rule or let's say, suppose if we let some u equal some function of x, okay, we'll call g of x, then the derivative, or by chain rule, if we're differentiating some function f that takes as its argument u, well, u is another function. This is chain rule. So this is going to be f prime of u, the outer guy, times dx u. Okay, that's not a multiple. It's just the derivative of x, derivative of u with respect to x, which leads us directly to the trig chain rule definitions. That the derivative with respect to x of sine of u, again with u being defined as this function of x, is equal to the cosine of u times the derivative of u. And this just goes down the line of our trig functions. The derivative of cosine of u is the negative sine of u times the derivative of u. The derivative of the tangent of u is equal to the secant squared of u times the derivative of u. And then our remaining guys, the derivative of the cosecant of u is equal to the negative cosecant negative cosecant of u cotangent of u times the derivative of u. The derivative of the secant of u, where u is again a function of x, is the secant of u times the tangent of u times the derivative of u. And then finally, the derivative of the cotangent of u is the opposite of the cosecant squared of u times the derivative of u. So it behaves just how we expect it would, just the chain rule, but this is kind of a nicer notation to use. Okay, so let's jump straight into a couple of examples. Again, we've already seen one of them, but it's always good to see some more. So example 3. Find the derivative of f with respect to t if f of t is equal to the tangent of 3t squared plus 2t's. Okay, so clearly this is a composite function. It's not just the tangent of t, it's the tangent of 3t squared plus 2t. So we should expect the derivative of this will not simply be secant squared t. Okay, there's more going on here. And if we want to be kind of formatting it like this, and we don't have to, eventually I'm going to expect you to be able to do this without explicitly defining this, but what's going on here is that u is this function 3t squared plus 2t. And so if it's helpful to think of f of t equal to the tangent of u, then according to our definition up here, the derivative of tangent of u will be secant squared u times the derivative, sorry, this should be a t, derivative with respect to t of u. okay? And then we just do it. So in other words, our derivative is the secant squared of 3t squared plus 2t times the derivative with respect to t of 3t squared plus 2t. So secant squared of 3t squared plus 2t. The derivative of this guy is 6t plus 2. And if we want, we could rewrite this a little nicer, I guess. We could maybe say that this is twice 3t plus 1 times the secant squared of 3t squared plus 2t. It's usually nice not to have things after a trig function, just to keep clear what is in our argument and what is outside of our argument. This is outside. Okay, chain rule, trig, no big deal. Okay, we'll do one more example of this and then jump into simple harmonic motion, which itself will include some chain rule with cosine and sine, so we'll get some more practice as well. But this will be example 5. This is a fun little problem because it will induce a double chain rule, which is just like, usually you have to pay extra for that kind of thing, but we're getting it for free. So they're asking us to find the derivative with respect to x of secant to the 4th, of 2x squared. Yeah, good stuff. So I think for our purposes, it will be helpful to write this as a product, if you please. Or no, I lied. We're not going to write a product, but we're just going to be explicit about what's going on here. Because oftentimes I think with the trig stuff, like secant squared or secant to the 4th, we fail to conceptualize that this is actually the secant of 2x squared raised to the 4th. We just kind of have this special notation that we use just with the trig functions where we slide that exponent in. But this is really what's happening. So this is a composite function. Our outer function is the quartic function. Our inner function is the secant function. But where the fun happens in this example is that our inner function is itself another outer function. Layers, man. And the inner function of that function is 2x squared. So we're going to get like a double chain here. It's going to be a lot of fun. So let's do it one little step at a time. The first level of the chain rule, we'll do the outer level of our quartic function. So the 4 drops down. We get secant squared, secant of 2x squared. The 4th becomes a cube. And then we need to take the derivative of the inner guy, secant of 2x squared. But to take the derivative of the inner guy is itself another chain rule because we have our outer function is secant, our inner function is 2x squared. So that's fun. 4 times the secant of 2x squared cubed. Taking the derivative here, the derivative of secant is secant tangent. And so we get secant of 2x squared tangent of 2x squared. Chain rule tells us to take the derivative of the inner part, 2x squared. Oh, yeah. You kidding me? And so then rewriting this, we get 4 times secant of 2x squared cubed times secant 2x squared tangent 2x squared. The derivative of 2x squared is 4x. And then making this look pretty, we're going to take this 4x out front, make this a 16x. We're going to see that we have secant of 2x squared cubed here and secant of 2x squared. multiply another one, this becomes a fourth, which we can write as secant to the fourth of 2x squared times the tangent of 2x squared. Huh. That was kind of fun. The derivative of this thing ended up being involving the function itself. And that's going to be a little bit important here when we look at simple harmonic motion, that when we differentiated this, we actually got a derivative that included the original function. And there's other stuff too, but that's kind of cool. Okay, so that is trig stuff with the chain rule. Doesn't get much better than that. All right, so now deep breath, shake it out. Take a sip of coffee. If that's your thing, you probably shouldn't be drinking coffee at 16. I didn't drink my first cup of coffee until I was sophomore in college, I think. Hold off. Now I can't live without it. I love it, but I can't live without it. So shake it out. Maybe press pause. Go take a walk. Because simple harmonic motion is going to be, it's kind of like rectilinear motion. It's like, this is strange. This is like real world, but it's strange. But we'll be okay. I'm gonna like dedicate a whole new page just because I can. And then I'm not actually gonna use this page because that was a weird binder thing behind here that, see the line there? It's hard to read. Oh, made it to the second section of my notebook. Wow, big deal here. But simple harmonic motion deserves it. Oh, dagnabbit. Oh, maybe it's designed to do that. The little divider thing came out. Oh, go back in. Easy. Don't worry. Crisis averted. I know you're worried. I guess we gotta take those out. Huh. Okay, so here we go. I'm going to give you a definition that might not make a ton of sense as you're writing it down, and that's okay. Sometimes that's life. You write something down, you don't know what it means, and then it slowly starts to make sense as you do more and more with it. So this is going to file under one of those circumstances. And what we're writing down is a definition of simple harmonic motion, which to me is kind of a misnomer. It's not that simple. There's a lot going on here, but we're dolphins. We're fine. Fins up. We'll get this. And here's the definition of simple harmonic motion. Oh, did I just trip on this? No, so much going on. Is my hair dripping? Yeah, whatever. I went for a swim earlier today at lunch. Mr. Rosa, Mr. Stinson. It was lovely. Nice to get some exercise at lunch. But now I'm tripping onto my notes. Okay. Describes the movement of an object Okay, so far so fun. Simple harmonic motion describes the movement of an object. We can follow that. We're okay with that. Slide this that way. There we go. On a line, okay. So far it's kind of sounding like rectilinear motion. Kind of similar. Okay, so now we're going to get into Looney Tune land. Okay, so movement of an object on a line. The example that I'm going to show you in a second specifically is like a weight going back and forth on a spring. So picture that. You got a weight, you pull it, and it starts going like that, either vertically or horizontally. Doesn't matter. So it's on a line, and then here's what makes it simple harmonic. That the measure, or when the measure of its acceleration, there's not two L's in that word, my apologies. Acceleration is always proportional. Oh, we love proportional. To the measure of its displacement from a fixed point on the line, and this is what makes it simple harmonic, its acceleration and displacement are oppositely directed. Oh, oh, yeah, I know. Okay, we'll get through this. We'll get through this. So something's moving along the line. Sounds like rectilinear, but it's a specific kind of rectilinear motion where the acceleration of the object is proportional to how far away we are from this fixed point. And in addition, the acceleration, when it's slowing down, and I shouldn't say that, the acceleration is oppositely directed from the displacement. So it's always working in the opposite direction from where your particle is, or from where your object is in relation to the fixed point. Okay? So if the object is above your line, the acceleration is moving down. If the object is below your line, the acceleration is moving up. Okay, it's always working opposite. And then before we get into like the kind of specific common example, the ways that this is often described by a function are with sine and cosine. So described by the functions f of t is equal to a times the sine of b times t minus c, or f of t is equal to a times the cosine of b times t minus c, where f of t is the displacement of the object after t units of time, and a, b, and c are constants. Okay. So simple harmonic motion is governed by trig functions, which in the example we're about to do with the movement of a weight on a spring makes sense, okay? Because if you release a weight on a spring, and if we're in this perfect world with no friction or air resistance, it's going to continue to move back and forth, up and down forever and ever in a cyclical manner. And the wonderful thing about our trig functions, specifically the cosine and the sine, is that they're cyclical. They just keep repeating the same values over and over. Just keep going around the unit circle, and the sine keeps getting bigger as the cosine gets smaller and smaller and smaller, and then the sine gets smaller as the cosine gets bigger and smaller. And it just keeps going. Okay, and so it's a perfect way to describe this motion of an object that keeps hitting the same values, hit the same max, hit the same min, and then moves between those values forever. Simple harmonic motion. Okay, and so at this point, I've sort of described one of the situations where simple harmonic motion is in play. So let's draw that out. The common example is a weight suspended vertically on a spring. This works just as well with a weight horizontally on a surface, you just have to pretend that there's no friction against the surface. So this works both ways. But it kind of just, I think we can picture the weight on vertically a little better. So basically what we're going to draw out here is the three possible states of our weight, okay? The first of which is the neutral state. That if you just kind of didn't touch it, it's eventually going to find some natural resting place. Where it's just sitting. Okay, so this is like the ceiling. That's the ceiling, this is the weight. And it's just happy there, okay? But there are two other possibilities for where this weight can be. If you took the weight and you pressed it up towards the ceiling and compressed that spring, maybe draw some tighter coils here. We've now created some distance away from this natural resting spot. Okay, and so if we're still using S as position or displacement, if you remember back to like rectilinear motion, now this distance from the resting point to the new position of the weight, this S is greater than 0, okay? The displacement is greater than 0. But you can kind of imagine when you've got this weight moving upwards, even though it's moving up, you've got this acceleration that's kind of slowing it down and ready to like blow it down. And so when you release that weight, you'll of course pass back through this neutral point, but then you'll reach the third possibility, which is now this guy is like getting sprung out and stretched out. And now the weight is below this neutral point. And so this distance, S, is less than 0, okay? But it's only gonna go a certain amount before the spring action gets too tense. And still you can kind of picture, even though we're moving down, because the coil is stretching out, the acceleration is moving against that motion until eventually it reaches its max stretching point, and then it springs back up towards the top, and it just continues that forever and ever. If we were tracking this S value, you know, like picture the sine. It would start at 0, and if you gave it this initial shove up, it would hit all of these values until it got to its max crunch point, and then it would stretch back down, and it would follow a nice curve that's cyclical and hits all of those values in between this max point and this minimum point. And we could at each point on our curve say, okay, our weight is above or below that starting point. That's kind of an example of simple harmonic motion. Okay. So now that we have like a physical picture of what's going on, we still definitely need to unpack part of this, or a lot of this definition. And the first part, I think, is probably the proportional acceleration, or acceleration as we wrote it here. What the heck does that mean? Well, if we remember back to, well, let's write this as a question. Proportional acceleration. If you remember back to 2.5, we said that the acceleration was the instantaneous rate of change of our velocity. Well, the velocity is the instantaneous rate of change of our position, our displacement, and so the acceleration is the second derivative of our displacement. So if we, for example, we're only going to do this for the sine version of this, but it works just as well for the cosine. If we let the displacement or the position function be f of t equal to a times the sine of b times t minus c, then f double prime of t, the second derivative of our position, is acceleration. So with this just very general form where we don't have placeholders for a, b, or c, we're going to take the derivative and then take it again and see if we can somehow show that the result, the acceleration, is proportional to this. It needs to be proportional to the displacement, which means it needs to be an expression that involves this original function times some constant. Okay, if two things are proportional, their quantities only change by a matter of a constant. So let's see if we can do that. First with f prime, first derivative, f prime of t, and this is where the chain rule of trig functions will come in. We're going to take the derivative of this guy. So this will be a chain rule because the argument here inside of sine has a t. This is a function of t, and so we're going to have to take the outer derivative of sine and then the inner derivative of b times t minus c, which is just a linear function, so it won't be too bad, but we have to do it nonetheless. So f prime of t is going to be equal to a, the outer derivative on the sine function is cosine of b times t minus c. We don't touch that in the first derivative, times the derivative with respect to t of the inner guy, which is b times t minus c. Okay? Well, the derivative of b times t minus c, the c, if we distribute this through, we'll just do it in our head. This is bt minus bc. bc is a constant, because b and c are both constants. So that just goes away. And really, we're just differentiating bt. So just picture like this is 5t. Maybe b is 5. The derivative of 5t is 5. So the derivative of bt is just b. Okay? A linear derivative is just the slope. And so this turns into ab times the cosine of b times t minus c. First derivative. Now we'll do that one more time. Take the derivative of this guy, which is in turn the second derivative of f. So we'll repeat the process. And I'll be really clear what's happening here. Or will I? No, I'm just going to walk you through it because the same exact thing is happening. We've got this outer function that's cosine. The inner function is, again, b times t minus c. So we know what happens here. We'll take the derivative of cosine, which happens to be a negative sign. So negative ab times the sine. So the negative comes from the fact that the derivative of cosine is the opposite of sine, times b times t minus c, times the derivative of b of t minus c, which we just did right here and said was b. So in fact, I'm not even going to write it here because this is just going to be a b. We've already got a b here, so this turns into b squared. So negative ab squared times sine of b times t minus c. So the thing we're trying to show is that this thing is proportional to that thing. We're pretty darn close because there's definitely a lot of things here that are the same there. Let's just rewrite this a little bit. We'll call this negative b squared times a sine of b of t minus c. Ho, ho, ho. So you're telling me that the second derivative, the acceleration of this object, is just negative b squared times its displacement? Look, that is that. What? Well, what's negative b squared? Slow down, Mr. Smith. Just a constant, okay? It's just some number. Could be 7, could be 12. I don't know. It could be anything. That's what variables are for, because it could be anything. So negative b squared is a constant so acceleration, I forgot to see. I'm really bad at spelling acceleration. Should probably work on that. Acceleration is proportional to displacement. But that's only half of it, okay? We got the proportionality and we're happy, but then remember, I'm gonna pull this back up, and the acceleration and the displacement are oppositely directed. Does what we just computed guarantee that? Oh, heck yeah, it does, because negative b squared is always a negative quantity. No matter what b is, whether it's positive or negative, you square it, it becomes positive. And then you hit it with an opposite, it's always negative. So this acceleration always takes the opposite sign of whatever your displacement is. So if your displacement is positive, your acceleration is negative. If your displacement is negative, your acceleration is positive, which is what was part of our definition. They have to be oppositely directed. So, and because b squared, sorry, negative b squared is always negative, acceleration and displacement are oppositely directed. All right. All right. Okay. So that's a big lead in. So now we're going to work, I think, just one example and then shoot you off into the world and hope you don't die. Okay. Actually, one last thing before we jump into the example. If you recall back to your study of trigonometry, which maybe is not that strong, if we're looking at a trig function of this form where you've got like an amplitude going on and maybe like a stretch and even a phase shift, there's like a lot going on here. There's some things about the graph that we care about. Specifically the amplitude and the period are really important. So how tall it gets and how quickly it goes through one set of all of your values is important. And so kind of the shortcuts to find those two things, not really shortcuts, they're just facts about the function, is that A, that number out front, is your amplitude. Because remember, the sign, no matter how weird we get inside of it, is always going to be between 1 and -1, and the cosine as well. And so this number A out front is what determines how tall and low you get. Okay, so if it's 5, you're going to vacillate between 5 and -5. If it's 1/2, between 1/2 and -1/2. That's the amplitude. The period is a little bit trickier. Within normal period, we know that we go through all of our values in 2 pi radians. Okay, once around the circle, we've hit all of our sine and cosine values. When we throw in this little b guy, he's either going to speed us up or slow us down. Okay, which is going to increase our period or decrease our period. And so basically, we're going to take our standard period of 2 pi and just divide it by b, where if b is speeding it up, a big number, it's going to cut that 2 pi into a smaller piece. And if it's slowing it down, dividing by that slower number will stretch out our period, okay? So 2 pi, the period is determined by 2 pi over the absolute value of b, just so that it doesn't really make sense to talk about a negative period, because it's time. I know you're going to go, well, Mr. Smith, we had negative time in rectilinear motion. Yeah, okay, but sue me. In this case, it doesn't make sense. I'm allowed to contradict myself. That's why they pay me. And then if we want the frequency, like how many times it goes through in a second or a given unit of time, our frequency is just 1 divided by our period. It's often called n, 1 over p. Okay. This is enough to make us dangerous. So let's tackle number 7. We can do this. Be confident. It's not that scary. It's just math. At the end of the day, it's just math. Yeah, less than like, this might be under, not gonna push it. Might be 45 minutes. Not bad. Not bad. To learn something you had no idea about before 45 minutes ago, that's pretty good. So, example 7. I'm so looking forward to having you guys in the classroom. Holy moly. These are getting weird. I feel like Tom Hanks in Survivor. That's not what the movie's called. Castaway. I'm gonna start talking to inanimate objects pretty soon. Wilson! Have you guys seen that movie? Really good. Tom Hanks. Don't get me started on that guy. I would love it if he was my uncle or something. Anyway, a weight. You notice how I didn't say dad? Because I have a good relationship with my dad. I don't want to replace my dad with Tom Hanks. But if he was just an uncle, you can add an uncle on here and there. I still love my uncles. It'd be nice to have an uncle that was Tom Hanks. Oh yeah. A weight vibrates vertically. Just means moves vertically. According to S, so now we've reintroduced S, which means displacement, which means position. 8 times the cosine of 1/3 pi t. Oh, joy. They didn't give us a C value here. That's nice. No phase shift. So we're going to just do some stuff here. What do they want us to do? A, find the velocity and acceleration for the motion for any t. Yeah, sure. So part A, velocity and acceleration. Basically, we're going to do this and then kind of confirm that this is actually simple harmonic motion. Because it's not just any, well, actually, that's not true. Any cosine or sine function describes simple harmonic motion, but it's nice to confirm it too. So velocity, we know, is the first derivative of s with respect to t, which for us, we're going to differentiate this guy. Chain rule all the way. So the outer function is cosine. So the outer function differentiates into the opposite of sine. Keep the 1/3 pi t all intact in the argument. And then chain ruling this guy, because this is a different function than just t. The 1/3 pi ensures that. But it's an easy thing to differentiate. It's just a linear function. And so what pops out here when we differentiate is pi over 3. Okay, the derivative of 1/3 pi t is pi over 3. And so we can write this as negative 8 pi over 3 times the sine of 1/3 pi t. That's our velocity. So our acceleration is the second derivative, or the derivative of our velocity. I should have said that the other way. The acceleration is the derivative of our velocity, in other words, the second derivative of our displacement. Which means we're going to differentiate this guy now. Still chain rule in effect here. The outer function is sine, which means its derivative is cosine, just regular cosine. We get negative 8 pi over 3 times the cosine of 1/3 pi over t. But again, we need to chain rule this inner part. So what pops out is a pi over 3, which means that this derivative is equal to negative 8 pi over 9 times the cosine of 1/3 pi times t. Cool. Cool, cool, cool. Okay. So we're just applying 2.5 velocity acceleration and now using the chain rule. Kind of fun. The follow-up question to what we just did is A, acceleration, proportional and oppositely directed to S, our displacement? Well, let's see. So what we need to show is that our acceleration is our initial position equation times some constant number, and that number is always going to be negative, because that will ensure that our acceleration always has the opposite value as our position. So let's do a little rearranging here. I think we can see that this is going to work out. We can kind of see that hidden in here is 8 times the cosine of 1/3 pi t. But let's tease that out a little bit. We had said that the acceleration in part A was negative 8 pi over 9 times the cosine of 1/3 pi over t. So we just need to make this look like it's supposed to. So this is equal to pi, negative pi over 9, that's important, times, we're going to shift this 8 over, 8 cosine of 1/3 pi t, and oh happy day, this guy is S, so this is in fact negative pi over 9 times S, our position. This is proportional, and this negative sign ensures that if S is positive, our acceleration is negative. If S is negative, our acceleration is positive. Okay, so they are both proportional and oppositely directed. Check, check. And then part C, find the amplitude, period, and frequency of the motion, and then we're going to get out of here. Yeah, we are. Yeah, we are. C, we want to find amp, period, and frequency. So let's just note that for S equals 8 times the cosine of 1/3 pi t, let's just pull out those ABC values. A is equal to 8, B is equal to pi over 3, and C, there is no C, is equal to 0. So just applying what we reminded ourselves of on the previous page about how to do amplitude and period and frequency. Amplitude is A, period is our 2 pi divided by whatever B is, and frequency is 1 divided by what period ends up being. So easy, we're fine, we're good. So amplitude. And you know, I do recognize that there are multiple A's flying around here. We've got A for amplitude and A for acceleration. This is A for amplitude. Amplitude is equal to A, which is equal to 8. Oh, did they give us a unit here? Centimeters. S is in centimeters. Sorry about that. In centimeters. So our amplitude is specifically 8 centimeters. Our period, well, the 1/3 is going to stretch out that 2 pi. It's going to make it a longer period than we're used to. Specifically 2 pi divided by pi over 3, which is 6. And this is seconds. So this is the time for one complete vibration. Or one complete vibration is starting at the neutral spot, all the way up to the top, back to the neutral spot, down to the low, back to the neutral spot. Picture the sine curve or the cosine. So cosine means it starts at the top and then goes down to the neutral spot, down to the spring, up to the neutral spot, back to the high spot. Just picture your trig functions. And then our frequency, the last guy, is 1 over the period that we just figured out, which means 1 over 6. So in other words, 1/6 of a vibration per second, which makes total sense. If it's 6 seconds for one vibration, if you count off a second, you've gone 1/6 the way through. Okay, we're going to call that good, whether you agree or not. It's a matter of individual opinion, but I'm ready to stop talking. I'm sure you're ready to stop listening. So let's press stop on record and bring any questions you might have to the next time I see you in class.